Well, good morning. So, yesterday, it was yesterday, right? Feels like a week ago. I kind of poured on you a lot of information which may seem useless from a practical point of view, like solving problems. However, I personally believe that thinking scientifically is more important than just being able to solve practical problems. And people who think scientifically should be recognized like athletes or actors or other celebrities. So I'm just giving a chance to everybody to get into that. That's what we need to know for the practical reasons for solving problems. When we have a solid, rigid object and many forces act on it, but it has axis, it's nailed, and it can rotate about that axis, each force is responsible for its own torque it generates. And if we add all individual torques together, that gives the net torque, and net torque is responsible for angular acceleration. But the shape, the mass distribution inside of an object also affects due to inertial properties and affect differently depending on the shape. We're going to talk about it. But quick preview. Let's say you have a hollow cylinder and a solid cylinder which have exactly the same mass and size. If they have exactly the same mass, that means here all mass was shifted toward the rim, and here it's evenly distributed, but the mass is the same, 500 grams. So according to these equations, conveniently proved for us, this could have been a disk or a cylinder. The height doesn't matter. This object has rotational inertia about the axis traveling through the middle point equal to a half of the product mass and the radius squared. But this one doesn't have this coefficient. So this has inertia twice more than this one. So if we apply the same torque, this is more inertial, which means in a second or 10 seconds, this will not spin as fast as this one because it provides less resistance to that influence. So this is the meaning of those variables, rotational inertias. They demonstrate how inertial an object relative to rotational action of a torque. We'll do more examples later. Now, this slide is to add an equation to what I just said. So if we have, let's say, a cylinder, and we're applying a force, like a string, this force, and if there is nothing else, this force generates the torque. And according to a definition, which I will remind very soon, it will be equal to this product. This is a very simple situation. Everything is perpendicular to each other. In this situation, if we apply the definition of the torque straightforwardly, the y component of the force is equal to the force itself. And this is the point of application, that the axis of rotation, r, represents that distance. In this situation, this distance is equal to the radius of the cylinder. So, and if nothing else is acting, responsible for rotation, acceleration should be equal to torque over this variable. And you can see Depending on the shape, this variable might be larger or smaller, and even if the torque is the same, it affects the angular acceleration. So if rotational inertia increases and torque remains the same, that decreases the acceleration, angular acceleration. We had exactly the same relationship for an object traveling straight ahead. Linear acceleration was equal to net force over mass. So more inertia, harder to change the state of an object. That's it. Nothing new here. We're just adding an extra word, angular or rotational. So this is an official definition of a torque of a force relative to specific axis. And we know that the direction depends on the effect it provides. If the force tries to move an object counterclockwise relative to the axis of our choice, we say it has a positive component relative to z-axis. And remember, z-axis is the one which is perpendicular to the screen or to the page. And again, it's very important to remember that this word, torque, it's a shortcut which represents a much longer sentence. A torque of a given force, specific force, relative to a specific axis. Only when you can say this sentence together as a whole, it makes sense. If you forget, if you miss any part of it, if you don't specify a force or an axis, it doesn't make any sense. Now, when net torque is 0 and the object is initially at rest, it remains at rest. Or we can use it backwards. If we see that the object is at rest, that means it's in equilibrium and net torque has to be equal to 0. And this equation, which provides a mathematical description of the statement net torque equals 0, has a name, torque balance equation, or TBE, because it says in equilibrium, all clockwise torques and counterclockwise torques should balance out each other. And the word balance also means mathematically cancel out. And that's what we have to finish. So we start from calculating an individual torque, then we're going to move to more torques, and et cetera, et cetera. We finished this problem, and we found the torque relative to the hinge. The axis was chosen for us at the hinge. Now it's the same object, the same forces, but we shift the axis, we choose it at a different location, and the question is, how will that affect the torque? Well, first, there's a question for you. I'm going to go a case by case from A to B to C to D, but you, at the same time, should jump to the case D. Not calculating anything, but just stating what do you think about the direction of the torque. Will be it positive or negative? All right, so I'm doing my part, you're doing your part. Of course, when we need to calculate something, anything, we have to start from a definition or a law. In this situation, a definition of an individual torque. And again, the definition tells us the magnitude should be equal to this product. The magnitude of individual torque generated by an individual force about a specific axis is equal to the product of two variables, r and fy. R represents the distance from the axis of rotation to the point of application of the force. And it's much easier to say in Russian. And Fy represents the component of force perpendicular to that line which connects the point of application of a force and axis of rotation. And you have to remember it word by word. It doesn't require understanding. Now we have to apply this. So case A, well, of course, I redraw the picture. We neglect the distance between the doorknob and the edge of a door because we told so. So the force is applied right here at the right end of a door. And the magnitude of this force is equal to 5 newtons because we have eyes. And the axis for calculating torque has to be chosen where? At the doorknob. That's the axis. Now the door is 0.9 of a meter long. And now I have to calculate the torque of this force relative to this axis. So again, a definition tells me to multiply two numbers. So you have to be able to make a statement about two numbers, number 1, number 2. So please tell me, what do you think about this number? Yes? So that's a very good hypothesis. So it could have been 0.9 meters. Please, anybody else? If you agree, of course, you don't have to say anything. But if you disagree and have a different number in mind, please tell me your different number. Anybody? Any number is a good hypothesis. Yes? Anybody? You moved. Now you moved. So please tell me a number. Different number. Again, remember, R represents the distance from the axis of rotation to the point of application of the force. So you have to take a pen or pencil and draw two dots. One dot represents the axis of rotation. Second dot represents the point of application of the force. And you have to look at those two dots and make a statement about the distance. Yes? Very good hypothesis. Although it's a distance, and distance technically cannot be negative, but I'm happy you gave me a different number. So please, I'm still waiting. I need more. So please take a pen. By now, you could have already made a copy and of this picture, and the copy should show two dots, two tiny points. One represents the axis of rotation, and we cannot change it because we told what axis is supposed to be used. The axis is supposed to be used at the right end of this line, door, object, no matter how you call it. And the second dot should represent that location, that point where force is acting, attached to that object. And then you have to look at your picture and make a statement about the distance between those 2 points. So we've got from left, from the middle, someone from this area. Please tell me a number different from 0.9 or negative 0.9. Please tell me a number. Well, you see, you have no pictures. If you ever been to my office hours, if you have no picture, I'm not going to start talking to you. Because picture worth how many words? 1,000. If you have no picture, you cannot solve this problem. If you're not trying to solve this problem, well, I'm really not sure if this time is really helpful. You have to try. I see the picture. Would you please tell me, show me, where is the axis of rotation? Where do we have to choose it according to the description of the problem? The axis is a point. You cannot move it. So you have to. So relative to the doorknob. Doorknob is located at the right edge of the door. So where is that location? So draw a thick dot, represents, okay. Now, where is the point of application of the force? That very point, you could have had a nail and then a string attached to it. So you would pull on that string. So where would be that nail? And again, that's a location, that's a dot. It's a nail, it's a very tiny thing. And that blue arrow, in case A, represents that force. And you can see where it begins. The arrow begins at that location, which has a name, point of application of the force. So where does it begin? And everybody has to do the same action. Where does a force begin? Case A, top picture, the blue arrow, which points up. Right here, exactly. Now please tell me, what is the distance between these two dots? What do you say? Do you see any distance? Is there any distance? No, you have to look at your picture, because this screen doesn't matter anymore. You have two dots, 1, 2, and you look at your picture and you can make a statement. Do you see any distance between those two dots? Do you? No. Okay. If there is no distance between those two dots, what number does it represent? What number? 0. So that's my third number. And now we have 3 equally interesting hypotheses. 0.9, negative 0.9, 0. Now, yes? We have to solve a problem we have to solve. We could solve a different problem, but that would be a different problem. And if we solve a different problem, we don't get credit for the problem we have to solve. We have to solve this problem. Relative to the doorknob tells us where do we have to choose the axis, at the doorknob. So that's the only reason. So now please, if you think this number for this calculation should be 0.9, please raise your hand. If you think it's negative 0.9, please raise your hand. If you think it's 1, okay, if you think it's 0, now you know. Thank you. So it's really hard to draw two dots, one on the top of another, and see two dots. But, well, this is one of the options. Yeah. Just make it a little bit different. But this is our axis. Not because we want to, because we're told to. And this is the point of application of the force, because that is a given. Now we look at this picture. I don't see any distance between these two dots. So 0 distance times 5, 0. And Newton times a meter. So this force has no torque relative to this axis. That's it. Any questions? But this force had torque equal to 4.5 relative to a different axis. So the choice of the axis matters a lot. Now, moving on. The force is here, but the axis is still there. The force is located 2/3 of the distance from the doorknob. But the axis is still at the doorknob, so torque will be equal to distance, which is 2/3 times 0.9 times well, 0.6, 0.9 over 3.3, 0.63, 3, right? You have to check me. Case C. So please draw the picture again. Draw a dot which represents the axis of rotation. Draw the force which is acting. Draw a dot which represents the point of application of the force. Look at your picture. Write the expression for the magnitude of a torque and make a statement about each number, each value of each variable. For example, R. What number should I write for this distance, please? Please tell me, what number should I write now for R? Case C, picture, the lady in the red shirt. I don't know your names, of course. What? 0. Because again, we have no distance between those two dots. So actually, the magnitude of this force doesn't really matter anymore, still 0. And finally, case D. So by now, everybody should have entered already a certain choice. About the direction. The most popular answer is number 1. So first, of course, we need to redraw the picture. I just like drawing something like this because the shape of the object doesn't matter in this situation. We just need to see two dots, axis, point of application, axis, point of application of a force. We can draw the vector which represents the force, of course. And we know that the magnitude of this force equals 5 newtons. And we know that it makes an angle of 10 degrees. Why do I know that this is 10 degrees, not this one? Well, that's a rhetorical question, yes? We all know it cannot be 10, it's much larger. So the only choice for 10 degrees is this little angle. Well, how do we calculate the magnitude? The magnitude of torque should be equal to the product of two numbers. This is, again, 2/3 of the total distance. We can see, we have eyes. 2/3 of 0.9. And to calculate the vertical component of a vector, first we must see that component. We don't see it there, so we have to draw it. First, we have to draw both components, just in case. The component which is, well, parallel to the line which connects axis of rotation and the point of application of the force doesn't provide any rotational effect. It tries to extend, expand, or maybe squeeze the object, but it doesn't rotate it. Only component which is perpendicular to this line responsible for the rotational effect. So the magnitude of this component will be equal to hypotenuse times a certain function of this angle. What function? Sine. So you have to be confident at this point what function to choose, because we've been using right triangles for 3 weeks in a row already. So now we just have to plug numbers in. So that's going to be 0.6 times 5 times the sine of 10 degrees. I don't know, whatever it is. I don't know sines of 10. So that's going to be 3 times sine of 10, not 100. Years of being spilled by coffee make effect on this calculator. So 3 times sine of 10, 0.52. Yeah. Having coffee and calculators close to each other, sometimes dangerous. Well, now finally the question about the direction. On the screen we see a hint, and the hint says we have to imagine how would the object move if it would be nailed at the axis of rotation, and the only one force would be acting on it. The force, the torque of which we are analyzing. And this has nothing to do to physics. This has nothing to do to mathematics. This is completely solely based on our everyday life experience, common sense. You have that experience. That's not a question to you. You don't have that experience. You have to take a piece of wood, a nail, a string, and play with it to gain that experience. That's the only way to do it. So if you had an object like this, nailed it, pulled on the string, how would it rotate? We have only 2 choices to choose from, clockwise or counterclockwise. So someone, please tell me. If you have an object like this, that's the axis of rotation. It can spin about this axis, either relative to you clockwise. This is counterclockwise. And now you're applying a force. You're applying a force here, which has a vertical component up, like this. Now you have to look at it, and you have to say a word which represents the name of that motion. And you have to choose between CCW, counterclockwise, or CW, clockwise. So if you think that this object would move counterclockwise, please raise your hand. Don't look at anybody. Just follow your intuition. Don't stop middle point, you know. You started moving, just go ahead and move it. It helps to fire up extra neurons in the brain anyway. If you think it would move clockwise, please raise your hand. Now, clockwise means the component of this torque relative to the z-axis should be negative. So that's supposed to be the answer, which is number 3. There is kind of a mental procedure, mnemonic rule, which helps to figure out the direction of the torque. So again, we have the axis of rotation. We have a force which is applied at a certain point. A force, of course, is a vector. So like this. What we always can do, we can extend this vector in general in both directions. Extend means draw a line away from the head from the tail. This line has a name, actually the line of action of this force. The force acts along that line. Now we can imagine this line is actually a part of a large circle with the axis inside it. So a large circle with the axis, with this point inside. In order to help us to see that circle, we can even imagine that we are bending a little bit the ends of this line toward the axis. So what we get in the result is a direction of imaginary circle which demonstrates how does this force trying to rotate this object about this axis. When we look at this circle, we name it. We name that direction according to a definition. This direction has a name, clockwise. And then we make a transition from a name to the sign of that component. Works every time. Any questions? Because you need to know how to figure out the direction of each torque. Because some of those will be negative, some of those will be positive, and the net torque for an object in equilibrium should be equal to 0. Well, so, by the way, we just have proved that there is a second expression which we can use for calculating the magnitude of a torque. So this is what we did. You may have noticed it before, but I want to repeat the calculation one more time. That's our original definition of the magnitude. However, we used the right triangle formed by the force and its components. There's a triangle right here, the actual force and two components. We need only one. But if we use the geometry, we get an expression which also tells us how to calculate the magnitude of a torque. R represents the same distance we used before, distance from the axis of rotation to the point of application of a force. But now, capital F variable represents the actual magnitude of the force, and theta represents the angle between force and the line connecting axis of rotation, point of application. What do you want to use? The first equation, the second? I don't know. I actually use neither. I use the third one, which I'm going to derive right now. So we have an object. We choose the axis. Doesn't have to be the actual nail, the actual hinge. Any point can be chosen as the axis because nature doesn't have axes. Nature doesn't care about axis. Nature doesn't care about what we think about nature. So it's only for us. Then there is a specific force which is applied at a specific location. Now what we do? Geometry. If we start from our original definition, if we extend the vector of a force to draw the line of action, and then if we draw a perpendicular from the axis of rotation toward the line of action, that line has a name, the lever arm of a force relative to the axis. And that line is related to the distance from the axis of rotation to the point of application. bless you. And that relationship is provided by the right-angled trigonometry. Lever arm is opposite to this angle theta, so it should be equal to the hypotenuse r times sine of theta. So what we can do now? Well, first we can rewrite the expression number 2, which we just derived a minute ago. Now we can rearrange these variables. Well, force, then r, then sine theta. And now we can see that the product of the distance times the sine theta is equal to that new physical quantity, which has a name, a lever arm of a force relative to the given axis. So this is the third expression which we always can use for calculating the magnitude of the torque, the third one. So now we have 3. The original definition, the second one which has all 3 variables, magnitude of the force, distance, and the angle. And the third one, the shortest one, originally provided by Archimedes more than 2,000 years ago. We just need to remember, again, the meaning of each variable. This is the magnitude of the torque, and that's the only information we can get from this equation, magnitude. The information about direction comes from extra reasoning. This is the magnitude of the force, the actual magnitude of that force. But this is the length of the segment of the line drawn from the axis of rotation to the line of action of the force perpendicularly, which makes it the shortest path. So this is an official definition of a lever arm. Lever arm of a force represents the shortest path from the axis of rotation to the line of action of that force, shortest distance. Done with definitions, done with equations. So whenever we need to draw a lever arm, we have to follow these 2 steps. We have to draw the line of action of a force, and we have to draw that segment which represents the shortest distance from the axis of rotation to the line. These steps don't require understanding, they require literal following. That's it. So you see, again and again and again, physics doesn't require much of thinking. Whoever told you you have to think in physics lied. Well, let's practice. In fact, I'm going to give you a minute. Please copy a picture and draw a lever arm from the axis for the force of tension. I have a very similar device right here. So I'm just giving you time to finish the picture, to draw the lever arm. By the way, we say lever. In Britain, say lever. So this type of a device usually is used for different simple experiments related to torque acting on an object in equilibrium. So this rod this rod is in equilibrium. Yeah. It doesn't move, velocity is 0. it remains 0, so no acceleration. Angular velocity is 0, remains 0, no angular acceleration. So first of all, net force equals 0, but also, as we know, net torque equals 0. How many forces right now are acting on this rod? Gravity doesn't go anywhere, always points down. Here in the hinge, there is some kind of a force, has no special name, just hinge force. And here, the force due to the string. We can measure the magnitude. We can take a protractor, measure the angle. 30 degrees. You have no protractor, so you have to trust me. And the force is about 9 newtons. And we can play, we can see, for example, what would change if I hold the same rod in equilibrium, but the string now is vertical. We can see that the force is almost a half of the initial. Why? Well, because this force should provide vertical component equal to this force. And if the angle is 30, sine of 30 is a half. So this type of calculations actually prove the torque balance equation. Net torque has to be equal to 0. And if we want to, we can calculate this torque. We can do it using any of the 3 equations. We know the angle, we know the force, we know the distance, we can measure it. 30 centimeters. You have no ruler, so you have to trust me. And how would you draw the lever arm? Well, you have to apply the 2-step procedure. First, we have to draw the line of action, which is actually already in the picture. Well, technically, you should extend the vector in both directions. Now, you have to draw a short segment, which represents the shortest path from axis of rotation to the line. And this is my lever arm. Yes? I'm sorry, I made a mistake. She forced me. Wrong. Don't do that ever again. So perpendicular represents the shortest. That's the lever arm. Thank you. And for example, what would be the lever arm for the force of gravity? Force of gravity is applied to the center of mass. Relative to this axis, again, we should extend the vector of the force, and we have to draw the shortest segment, which should be perpendicular to the line of action. This line, which is equal to half of the length of the rod, is the lever arm for the gravity. If I shift the axis, and I always can, if I choose the axis here, what should you tell me immediately about the lever arm of the force of tension relative to this new axis? Lever arm of the force of tension relative to the axis of rotation chosen at the right end of this rod. Can you prove it? This is the axis. I just draw that dot. Where is the point of application of the force of tension? At the same location. Do you see any distance between these two dots? No. There is no lever arm at 0. That's it? Okay. Oh, I just did it. Two questions simultaneously for you. It's about the same force, but two different axes. The question number 3 asks you, what is the value of the z component of the torque of the tension relative to the axis chosen at the left, at the hinge, at the left end of the rod. And second question asks you what is the value of the z component of the torque of the same force of tension, but relative to the right end of the rod. So two questions at the same time. So again, a reminder, this is what this word torque means of a given force relative to the chosen axis. So the possible answers are the same for both questions. Question number 3. For the question number 3, the axis chosen at the left end of the rod. Question number 4. For the question number 4, the axis chosen at the right end of the rod. And question number 4 is easier because we just have it answered, right? That's the axis. That's the point of application. What number? Enter it. Question number 3. Okay, that's the axis. That's the point of application. And we need to look at the force. So we can apply our strategy, mnemonic rule, extend the line, bend it a little bit in such a way so the axis would be inside that imaginary circle. Now, the direction of the force tells you the direction of the motion that torque tries to do. And now we'll look at this picture. How do we call this direction? We write it down. That excites an extra memory cell. Counterclockwise means positive. That's it. And here, the answer is 0. And we have to repeat this type of reasoning every time when we need to when we need to analyze, calculate, find each individual torque generated by each individual force acting on the same object. So we use this fact already kind of in discussion when we have a small object. Force of gravity acts just at that object. We neglect the size of it. If we have a large object, we know it has a special point. We call it center of mass. The old name of that point is center of gravity because gravity is acting on that object at that point. And find the torque of the force of gravity relative to, we can choose any axis, and I want it here because we've explored all other options already. So the torque of the force of gravity relative to that that's not theta, that's O, relative to that axis should be equal to, if I use the third expression, magnitude of the force times the lever arm of that force. All I need is the lever arm of that force relative to that axis. How do we find it? A two-step procedure. First, we need to extend the vector of the force. That gives the line of action. Second, we have to draw a perpendicular from the axis of rotation to the line of action. Well, of course, it's implied that we have to look at that perpendicular now and make a statement about the length of it. And the length turns out to be equal to half of the length of the rod. That's how it works. Just follow the steps. So that's a summary. Individual torque, the net torque, the direction depends on the what type of rotational effect does torque make. It helps to look at the picture in such a way so we would see each force, because in that case we can also see the distances and the direction of each torque. And when the object is in equilibrium, net torque equals 0. Now, you may be confused sometimes if you read a textbook, because in the textbook, they very often use the same variable to two different things. This letter might represent the magnitude or a component. And depending on what it represents, the equation looks differently. The standard expression for the torque balance equation is this. The sum of all components on the left equals 0. But if you write it like this, each component has to be analyzed accordingly our definition, when it's positive, when it's negative. Some of these numbers are positive, some of those numbers are negative. However, sometimes people prefer show explicitly that this torque has a negative component or positive. If you write an equation in this form, each number here represents the magnitude of the torque. And if you do it like this, of course, you can simplify this expression, just move all the terms over there on the right-hand side of the equation. This is how originally it's been written. All counterclockwise torques are balanced out by all clockwise torques, and if you write it like that, each variable must be positive, must represent the magnitude of the torque. Well, question which you don't have to answer on a web assign. It's a very, very difficult experiment. Nothing. What do you say about the net force? Net force acting on this board. Two forces have the same magnitude and opposite direction. Look one more time. Nothing. Of course, net force, which is this plus this, equals 0. They cancel each other out. What about net torque? Well, we cannot calculate it yet. First, we have to add one specific element, which is what? Axis. Where can we choose the axis? Anywhere. So the easiest choice is here. And, well, neither of these forces have any lever arm, 0. So net torque will be equal to 0 plus 0 equals 0. You can ask, what would happen if the axis would have been somewhere else? Calculate it. Net torque still will be equal to 0. It will be equal to the counterclockwise torque from the top force plus the clockwise torque from the bottom force, which will have the same magnitude, but opposite direction. So this is just, again, an illustration what equilibrium means. Net force equals 0 because we knew that, and net torque equals 0 because we've learned that. What if we make things more complicated? More forces like this. Well, again, net force will be equal to this plus this plus this, 0. What about net torque? We can choose the axis anywhere, here for example. And net torque will be equal to counterclockwise positive from the force on the left plus 0 because it has no lever arm from the force in the middle plus negative clockwise from the force on the right, again 0. So this is another illustration of a general rule. When a solid object in equilibrium, first of all, net force is 0, of course. But more importantly, net torque is always also equal to 0. And very often we don't even have to use the condition about net force. The torque balance equation usually gives away the answer faster, more conveniently. Again, the same slide, with the same emphasis. We have two equations. Net force equals 0. Net torque equals 0. And the general strategy for solving any problem related to an object in static equilibrium, of course, starts from a picture. Then you have to draw forces. Then you have to choose the axis. Then you have to show each individual torque, calculate each individual torque relative to that axis, set the sum to 0, and then mathematics will tell you the answer. Well, first example. People have it done more than 2,000 years ago. That's the strategy, and we just have to follow the strategy. So what is happening here? A person can apply a force up to 60 pounds. But if that person uses a lever, depending on your pronunciation, that person can move or hold a much heavier object. So this is the force. Oops. This is the force the person can apply, 60 pounds. This is a fulcrum, a pivot, a support. People call it differently. And here is the weight the person can hold. And the question is, how heavy is it? What is the weight of this weight? Well, if the person is holding the weight, we call it equilibrium. Maybe slowly moving, still almost equilibrium, which means we can apply the torque balance equation. Torque balance equation, net torque acting on the object has to be equal to 0. The question is, which object? There is a fulcrum, the person, the weight, the earth, the sun, the stars, clouds, trees. For each object in the universe, we can write torque balance equation or Newton's law. We have to choose the right object. And in this situation, what is the right object? No. For the mass, first of all, it practically has no size. For the mass, we can write two equations. Of course, force of gravity and the normal force. It's in equilibrium. Net force acting on that mass is 0, for sure, but it doesn't help us, because this is what we're actually looking for the mass of this object or for the weight of this object. So we tried, it didn't work. Let's try a different object. Please tell me, you want to say something? No? You moved. Okay. What is another object in this situation which we could try? Please. You moved again. Say.
So you have the force from downwards.
What object should we choose for our diagram? You see the steps say picture, diagram. When we draw a diagram, we choose an object first. We tried the mass. It didn't work. So what is another object should we, yes, the lever or the board, yeah? This object. So what forces do act on it? Of course, there is a force, not really normal, but people still call it normal. Of course, there is a force applied by the person. And because of this weight sitting on another end, there's a force acting on the board from that weight, which is equal to the weight of that weight, which is we're looking for. Now, because the board is in equilibrium, we can write that equation, but first we have to choose what? We cannot write the equation yet because we have to choose what first? Axis. So choose. And the rule of thumb, not a law, rule of thumb, don't choose the axis at the location of the force you're looking for. Don't choose the axis at the location of the force you know. Choose the axis at the location of force you don't know and you don't care about. In this situation, what is that force which you don't know, but you don't care about? Yes? From the fulcrum, that normal force. So we choose the axis here. Why? Because we know from our previous experience, from examples we've done today, if we choose the axis here, the torque of that force relative to that axis automatically becomes equal to what? 0. So now the equation says, well, okay, so this torque is counterclockwise. This torque is clockwise. So I write this is the lever arm for the weight. This will be my lever arm for the applied force. So W, the unknown force weight of that mass, times the lever arm, 30 centimeters, minus 60 pounds times 150 centimeters equals 0. I don't even bother to convert pounds into newtons, centimeters into meters. First of all, centimeters will be canceled anyway, and my answer will be in pounds, so why not? So to calculate now, the unknown, all I have to do is this 60 times 150 over 30, 300 pounds. That's it. According to the legend, Archimedes was able to build so powerful devices they could lift a warship from the sea. Well, of course, we have to move to more complicated situations. So I'm going to give you a time to answer question number 5. I just want to give an illustration of what might be happening in this case. So we need pivot meter stick with some so those are hangers. No, how was it? Okay, got it. No. Okay, so, and this device also can be used to prove the torque balance equation, or to use torque balance equation to answer various questions. So what do we have in this situation? Only one weight attached to it over here. Okay, that shouldn't go down. Almost. So of course, the location matters. If I move it to the very end, there is a net torque counterclockwise relative to you. If it's too close, there is net torque in opposite direction. So there has to be a certain location when the meter stick will remain in equilibrium, which means net torque acting on the meter stick will be equal to 0. Yeah? So now, of course, so please keep answering the question. What do we have to do? Well, we have to, bless you, have to follow the strategy. Three forces are acting on the meter stick. Well, we can call it tension, yeah, which holds the stick. Here, there is a force acting because of the weight, and that force has magnitude of m times g, mass of the weight 0.1, times 10, 1 Newton. And also there has to be a force of gravity acting on the meter stick, and it's applied to the middle point of it. This is m times g, and the mass of the meter stick is what we are looking for. So we will be using the torque balance equation, and to do that, please don't get sick before the exam. Question number 5. All right, we have a distribution. To apply the torque balance equation, we will have to calculate each individual torque, torque number 1, torque number 2, torque number 3, relative to z-axis. And to do that, we have to choose what? Axis. Do you see any information about the axis? No. So the answer is no. There's no way to say anything about the torque generated by gravity yet. So in a case like that, you should have asked, what's the axis? So you would need an additional information, and I would tell you, pick one. Doesn't matter, it's your choice. And you should make a choice, pick the location for your axis, and tell it to me. So please, anybody, tell me, where would you like to choose the axis of rotation? Use your own words. I'm just killing time. I'm waiting for someone say something. Where would you like me to choose? Yes. Why would it be there? You said the axis would be. You know, to me it sounds like there is something which beyond us forces the axis to be there. It says that I want the axis to be there, all right? If anything goes wrong, that's her fault. But I would be doing exactly the same thing, because there's a force here. We can call it tension, which we don't know. We will find it if we want to, but we don't care about it. So the easiest way to eliminate the torque of that force is by choosing the axis at the point of application of that force. We cannot eliminate the force. The force is not equal to 0. But torque will be equal to force times lever arm, which is 0 for that specific choice of axis. So now we have left only 2 torques. So number 1, number 2, number 3. The torque number 1 will be counterclockwise with the magnitude of 1 Newton times 20 centimeters. The torque number 2 is 0 because of our choice of the axis. The torque number 3 will be equal to, well, first of all, it will be negative. It should be equal to the magnitude of the force, which is mg, times the lever arm. And this is a place where people make mistakes, but not because of the physics, because the picture is not very informative. For example, here, the picture tells me the lever arm of the first force, 20 centimeters. But the picture doesn't show the lever arm for this force. So I have to draw it. And it has to go from the axis of rotation to the line of action. And this green line represents the lever arm, which I have to use here. And now I have to write a number in these parentheses. Number for this distance. Can you tell me that number? Yes? How many? And, okay. So that's a meter stick. How long is a meter stick? 1 meter. And this point in the middle divided in half. So we have 50 centimeters to the left to it. We have 50 centimeters to the right to it. And the pivot is 30 centimeters away from the left end. So what's left is 20 centimeters. again 20 centimeters. So now 1 times 20 minus mg times 20 equals 0. mg equals 1 Newton, or mass equals 100 grams. So the last example encompasses many possible situations. Many. For example, I can use the same board with 2 scales. Let's make it 0, 0. This weight represents a weight or a person walking left or right or standing somewhere. And you can see that the location of this weight affects the readings differently. Of course, if we place it here, more weight goes there, less there, vice versa. Interestingly, what might happen if we move it further and further in one direction? So what's going to happen to this reading? Oops. So what happened to this reading? At a certain point, it became equal to 0. And if we move it even further, that's it. It tilts. In this situation, actually, we still can hold it, but we would have to apply the force downward. And of course, all we have to do is just draw a diagram accurately. Please use both halves of your brain, one to answering questions, second to following my work. So, a typical situation when we have 2 supports, a board, and a third object, an additional object on the top of the board. 2 supports, a board, and another object. So the bolt holds it here, prevents it from tilting. If the bolt would break, the whole board would start rotating in a certain direction. And that would be happening because the torque due to a person or a weight is stronger than the torque due to force of gravity acting on the board. There is also another force acting from a second fulcrum. And again, people call it normal force, normal number 1, normal number 2. This is force of gravity acting on the board, and this force is due to lady or another object pushing on the board. That's what we have. Now we have to choose the axis of rotation. And the rule of thumb tells us choose it at the unknown force. When in this situation, we care about all forces, but still we have 2 unknown forces. So this is my first choice at the left fulcrum. Now, in general, we have to write 4 individual torques. Number 1, number 2, number 3, number 4, torque 1, torque 2, torque 3, torque 4. For each individual torque, we have to make a statement, is it positive or negative, what its magnitude. Torque number 1, by my choice, equals 0, has no lever arm. Torque number 2, this one, for the second fulcrum, about the same axis, it tries to move the board counterclockwise, so it's positive. It will be equal to the magnitude of the force. And we don't know the value, but we always can write the letter, the symbol, which represents that variable, that value, times the lever arm. That should be the distance from the axis to the fulcrum. In my picture, this distance is given as 1.4 meters. Done. The torque number 3 is due to force of gravity acting on the board. Relative to this axis, it will be clockwise, so negative. The magnitude of the torque will be equal to mass times g. The mass of the board is 12 kilograms. G equals 10. The magnitude of that force equals 120 newtons. And now I have to figure out the lever arm. The force of gravity is applied to the middle point of this board. Middle point breaks this board into 2 halves. So the distance from the bolt to the middle point of the board equals a half of the length of the board, which is 3.9 over 2. And finally, the torque due to lady. So about that axis, the direction of that torque is clockwise, which makes it negative. The weight of the lady is a given number, 530 newtons. We don't even have to multiply m and g. Now we have to multiply by the lever arm, which is supposed to be distance from the axis to line of action, which is just equal to the length of this board, which is 3.9 meters. So now we have all individual torques prepared to be used in the torque balance equation. We have to write 0 plus the unknown force times 1.4 minus 120 times 3.9 over 2 minus 530 times 3.9 equals what number? You have to say it. Someone has to say that number. Thank you. How many unknowns do you see in this equation? How many unknowns? 1. So you do take your calculator and calculate that unknown force. Now, if you want to calculate the second unknown force, the one on the left, you have 2 options. It is up to you which you want to use. Number 1, you can choose a different location for your axis, for example here, and repeat the strategy. Or now you can apply the force balance equation. Net force has to be equal to 0. And since now you know 3 forces out of 4, you're done. Yeah. What you can write is negative normal force number 1 minus 120 plus the force you just have found minus 530 equals 0. Force balance equation. You should try both methods. Just to see they will give you exactly the same answer. Well, at the slide, and I'm just going to show the strategy. We don't have to do the equations again. So what do we do? Well, first we have to redraw the picture. Now we have to show the forces. Force normal 1, force normal 2, the force of gravity due to the weight, and the force of gravity acting on the board, which is applied to the middle of the board. And finally, the most important step, choosing the axis. I want it here. Why not? Relative to this axis, the torque balance equation says 0, because this force has no lever arm. Clockwise, minus mg times, that's supposed to be equal to 1/2 meter minus 20 centimeters, 30 centimeters. This number comes from geometry, from the picture. Now, this one, clockwise, so minus again, mg times, that should be this distance. We cannot switch to a different axis until we finish writing the equation. So all distances, all lever arms must be measured from the same axis. And this should be 60 centimeters. And now this, normal force number 2, provides counterclockwise torque, so plus normal force number 2 times, well, same point of application, same distance, equals 0. Now you can solve any problem related to static equilibrium, as promised.